Okay, everybody, let's get started. First of all, a very warm welcome to this webinar called Join the Nanoscale Resolution Revolution, where we will try to tell you a little bit about how you can use nanocomputed tomography for the understanding of novel functional materials in applications as batteries and semiconductors. My name is Emil Espes, and I work as an area sales manager at Excillum. However, today I'll be moderating this webinar. But as an area sales manager at Excillum, a big part of my job is to travel to conferences and trade shows and different events all over the world. However, as you know, this summer we'll not be able to travel to all of those events. And therefore, at Excillum, we decided to start this webinar series, where this is the first webinar. In this webinar series, we intend to invite thought leaders and experts in many different fields of X-ray applications. These experts, they might be external, as today when we're joined by our partners and users. But in the future, they might also be internal experts from within Excillum who comes and tells a little bit about their view on our technology and our products. But with that, let's get started with today. So this is the agenda of the day. We'll start by me saying a few words on Excillum and our nanotube technology. After that, we'll be joined by Christian Fella from the Fraunhofer Institute, who will tell us about the NT-CT, which is a nanocomputed tomography system that they've built up at the Fraunhofer. After that, Dominik Müller from University of Würzburg will come and tell us about how they have used this NT-CT for their research on some different types of materials. Lastly, Nicolas Westphal of the company Procon X-ray will come and tell us about how they have made this system commercially available for the general public. We'll then end the whole webinar with a short Q&A session. And I should also say that please do send questions throughout the whole webinar. You can either use the questions form or the questions window in the GoToWebinar software, where you can type in questions that are then sent to us, or you can send me an email at emil.espes@excillum.com. We intend to try to answer some questions during the webinar in text form, and then we will lift up a few questions in the end, which we will be discussing with the panelists. And if it is the case that we don't have time to answer your question, we'll follow up with an email to you afterwards. So we intend to answer all questions, so do not hesitate. Okay, about Excillum and the nanotube technology. So as you might know, Excillum, we are a company where we make X-ray sources. We were founded in 2007, and we're based in Stockholm in Sweden. We do also have a sales office in the US, and we're working with different partners throughout the world as well. We're a team of more than 50 people, and more than half of our staff are actually in the R&D department. So we're a company that's focusing a lot on development, on developing our product and technology. And we have two main product lines, the metal jet and our nanotube. And the metal jet you might be familiar with. It's based on a liquid metal anode technology, which results in the world's brightest microfocus X-ray source. However, today we will be focusing on the nanotube, which is based on our quite advanced electron beam technology, resulting in the X-ray tube with the world's smallest X-ray spot, which is ideal when you want to do high-resolution imaging, which is the topic of today. So the nanotube N2 is the latest generation nanotube, and this was introduced earlier this year at a conference in Austria. And the nanotube, it's a tungsten on diamond transmission anode or transmission target, where the target is the most protruding part of the tube. This means that you can get very, very close to your spot or your focus, as close as 100 microns in this case. You'll also see that the front of the tube is cone-shaped, which makes it possible to come very, very close with a nice and stable sample holder. And the platform also has a lot of built-in water cooling to ensure ultimate spot stability. Looking a little bit at the specification of the tube, The main specification of both the nanotube N2 60 kV and the nanotube N2 110 kV is the really high resolution. So for both tubes, you can resolve features down to 150 nanometers lines and spaces, which is illustrated by the Siemens star in this image, where the innermost features are 150 nanometer. You'll also see that this is an isotropic resolution, which means that you have the same resolution in all directions. And I should also mention that you can resolve this 150 nanometers throughout the whole acceleration voltage range. And while resolving 150 nanometers with the nanotube N2 60 kV, you can put 0.25 watts on the target. And for the nanotube N2 110 kV, you can put 0.75 watts at the target. With both tubes, you can also run with a larger spot if you want to put a higher power into your spot to do faster imaging or something like that. I also wanted to show you a little bit about how you can operate the tube. So it's a highly automated operation where you as the user can type in what spot size you want to use, which then would translate to what resolution you would need. So in this case, the user typed in 0.34 microns. And then when you click apply set points, the source will automatically set the required parameters and internally validate spot size, which is then reported to you as the user. So in this case, the achieved electron spot size was 0.35 microns. And this type of internal validation and reporting is really ideal if you want to do something like inline inspection with an automated defect analysis or something like that, where you need to rely on knowing your resolution so that you know that you're catching the defects or features that you are looking for. So that was very, very quickly what I wanted to tell you about the nanotube N2. And with that, I'll hand over to Christian Fella at the Fraunhofer Institute, who will tell us a little bit about how they have used this tube. So over to you, Christian.
Hey, thank you, Emil. Hello and welcome to my contribution. I will today talk about these contents. I will first introduce the Fraunhofer Nanosystems group. Then I will say some words about possible setups for Nano-CT. And finally, I will present our latest development, the NT-CT. We are part of the Fraunhofer Development Center X-ray Technology. It has locations in Fürth, Würzburg and Dengdorf. In total, more than 100 full-time employees work on topics related to tomography there. The sample spectra ranges from microscopic to really macroscopic samples like complete cars, as shown on this picture. We are located in Würzburg and currently 5 full-time employees plus students work in my group. Our main working area is the development of tomography systems. There we do complete system design, hardware and software. The focus, of course, is always on high resolution systems. We also do service measurements, including small angle scattering and all kinds of tomography. For this, we use our laboratory equipment and also synchrotron beamlines. Our third topic is data analysis and algorithm development, what we also offer as service for external. When we look at common geometries for laboratory CT scanners, you will find these 3 types depicted here. The first type is the so-called full field microscope, where you have an X-ray optical element. This element, for example, is a zone plate, is magnifying your sample on the detector, and here the resolution is given by numerical aperture of the optic and the X-ray wavelengths, and here you will reach around 50 nanometer. The other 2 cases uses projection imaging, where you only have your sample in between source and detector. Here you are either limited by your source size or by the pixel size of the detector. In general, the high magnification case has some benefits like simplicity, a flexible field of view, and the possibility to go to higher X-ray energies. Besides the here given values for resolution, in practice you have to keep an eye on the signal-to-noise ratio. Otherwise, you will not reach these resolutions. Since the work we here present is in the high magnification case or geometry, I will describe in the next slides which points we use or needed to ensure good signal-to-noise ratio. So for the high magnification case, we can benefit in terms of efficiency from the components we are able to use, and nanofocus sources reach higher brightness, especially in combination with the anode on a diamond substrate. The reason herefore is so smaller spots can handle higher heat load because the surrounded area is not that strong heated like for bigger spots. The second point, it's easy to obtain a large solid angle as long as you can maintain or obtain a small source sample distance, where we also had a focus on. On the detector side, we are able to use photon counting detectors because we don't need super small pixels. These detectors have the benefit that the detector is not adding noise to your measurement, and you only have your photon noise from your source. It has a high quantum efficiency, therefore nearly all photons are detected. And in comparison to conventional flat panel detectors, the point spread function is much better. This means you have less pixel blurring and you can avoid oversampling. So your resolution is close to your sampling. The design goal of the NT-CT was to have a compact setup that fits in every lab, a setup which is stable enough to also do relatively long measurements when they are needed. This in combination with state-of-the-art components, and for flexibility we want also have a variable field of view. As further main components, we are using the Dectris photon counting detector. It has a pixel array of 2000 × 500 pixels. The sensor material is 750 micron thick cadmium telluride. It has 2 energy thresholds, so you can use this as digital energy filter. The Excillum nanotube has, as already mentioned, reaches a smallest X-ray focal spot of 300 nanometer. The N2 now has 3 times more brightness, and it's also available as 110 kV version. The structured target ensures to verify the spot size and therefore to maintain in each measurement the full resolution, not only in your resolution test measurement. With these components, we are able to reach a periodic resolution of 150 nanometer in 2D and only slightly less in 3D. Of course, the 3D resolution depends how well the reconstruction and the image correction works. To ensure their good image quality, we use our own reconstruction that is developed around the components. And additionally, we are also able to adapt quickly to some special needs. Now I will give you a quick look into the software by setting up a simple CT scan. So what you can see now are the 2 screens of the software. So we have our main panel with the basic functionality, and we have our dashboard where we have our webcams and where we call dynamically sub applications like the reconstruction. The X-rays are in this case already on, and you see the live image of your sample, in this case a seed. Now the height is adjusted to the area where we want to measure, and now we want to place the sample inside the center of rotation. Therefore, we start this sub application, which takes automatically a few images and is calculating the positions. So what you have to do then is you select the area where you want to measure the sample, or you just leave the pre-calculated values and you confirm this. And what you now have to do, you move the sample closer to the position, to the source, to the position where you want to measure. So yeah, you can see it comes in. And then to start a CT scan, you have to create a sequence. Therefore, you just type in the name of the sample. You set the number of projections, and you also set the exposure time. In this case, 4 seconds to have a 2-hour CT scan. And then you're good to go. So you start your CT scan. What you can see now is the time lapse of this 2-hour CT scan, and you can see the data is reconstructed with the projections already recorded. And once it has finished, so then you just save your data to a TIFF stack, and you can then go on with your post-processing. So that's basically everything you have to do to perform a CT scan. That was my part so far. Thank you for your attention, and feel free to contact me by email if you have any questions. Then now back to Emil.
Thank you, Christian, and thank you for also showing how to operate your system. Before introducing the next speaker, I just wanted to remind you about that you can send questions to us throughout the whole webinar, and we'll be chatting and replying to some of the questions, and we'll take a few of them in the end of the webinar. And with that, I'd like to hand over the word to Dominic Müller, who will tell us about how they've been using the NT-CT for some different types of materials. So over to you, Dominic.
Okay, yeah. Many thanks for the friendly introduction. Yeah, my name is Dominic Müller. I'm a material scientist at the chair of X-ray microscopy at the University of Würzburg. I'm pleased to be able to present a part of my work in this Nano-CT webinar today. All right, let's get started. In my talk, I will present you a bunch of case studies where we are using the previously presented NT-CT system for non-destructive testing and materials research. Through our cooperation between the chair and the people at Fraunhofer, we have access to the advanced infrastructure there, so we can use their latest developments for our research. First, a brief introduction to my institute. Founded in 1402, the university is one of the oldest and now largest universities in Germany. One of the most famous heads of the university, of course, is Wilhelm Conrad Röntgen. On a Friday evening in 1895, he discovered here in Würzburg the X-rays, that also had been named after him in German-speaking countries. The picture here shows his original laboratory, with cathode ray tubes set up, which can still be visited today. This year is the 125th anniversary of his discovery, which is why the university has adopted the slogan 125 years of new insights. As already stated, I'm from the chair of X-ray microscopy, and there we are pushing forward current research with different X-ray techniques. In addition to the work on new Nano-CT setups and the scan of samples with our advanced CT equipment, we also deal with phase contrast imaging, we build equipment for small-angle X-ray scattering, and we develop new methods and algorithms for data reconstruction. At our chair, we have access to 3 machines for high-resolution Nano-CT. Each of them follows its own approach. The principles behind it you have just heard in the previous talk. Nevertheless, I would like to briefly introduce our 3 available devices. The XRM is based on an in-house rebuilt electron microprobe analyzer. Now we equipped it with a tungsten needle as X-ray target for a very small focal spot and high-resolution applications. The TXM setup uses the high brightness of an Excillum liquid metal jet source. The magnification is achieved by using modern X-ray optics, and there we are particularly pushing forward research with X-ray optics. But in this presentation, I will focus on samples that we have characterized with the NT-CT system. So, why we mostly choose NT-CT for materials research applications? We receive many requests from researchers of different disciplines with their samples, mostly very specific problems with which they have already failed on standard X-ray systems. For most requests from the field of material science, we then go for the NT-CT system. Even if the system does not offer the highest resolution available to us, the additional points in application outweigh this, and the resolution is much higher than with the widely used micro-CT systems. And for many questions, it can nevertheless compete with SEM analyzers. A big benefit is, of course, the large field of view, which also allows much larger samples than, for example, a lens-based nano-CT system. And thanks to the comprehensive automation, we can allow interested colleagues to work on the instrument on their own, after just a short introduction in order to perform their measurements. Okay. In the following, I have selected 3 examples that are exemplary for questions that are being asked in everyday business. So let's start with an example from the field of integrated circuits. Semiconductor components are subject to race to smaller and smaller but also more complex 3-dimensional structures. At the same time, however, a tool is needed to detect faults and defects. And of course, the data obtained in this way can also be used for reverse engineering. So, well, you often start with the obvious. And so we took a common micro SD card from the electronics store as a first example. SanDisk Ultra 32 GB current model, and then we scanned it with 98 nanometer sampling. And here we see a 3D rendering of the inner structure. You can see a lot of pillars and the center structure that looks like conductor tracks. And to put it in scale, this is not a simple electronic circuit board. We are looking at the internal structures in the semiconductor chip. This internal path structure has a width of 31 microns. So, what exactly are we looking at? In this image, the embedded metallic structures are shown, and we can examine them for insufficient metallization or defects. If we now take a closer look at one of these pillars are metallic wires, so-called through-silicon wires, and these connect the multilayer memory cells to each other. Each of them has a diameter of about 100 to 200 nanometer. These structures are essential for all modern and complex 3D storage systems. However, the resolution is even more impressive when we look at a single sectional image from the reconstruction. So let's zoom in a bit. You can see in the close-up that these individual towers are not uniformly round, but periodically and patterned with a longish or round cross-section. Now let's swipe to the right. If we take a closer look at the conductor path structure, we see that these also consist of individual turrets with a diameter of about 100–150 nanometer. You can see the resolution even better in the side view. We can now make virtual section through the sample volume. Here we can see the wires in the entire height at different positions. In all three sections, you can clearly distinguish between the single pillars in the structure. With a frequency of a few hundred nanometer, in the figure below they have a period of 600 nanometer. And you can also see parts of the horizontal conductors at the bottom. In addition, we can guess in the side view how the cross-section tapers toward the top. So let's rotate the cut. In the vertical view, we especially see the staircase-shaped connections in the edge region. This is the edge of the chip, where all layers are connected to the base plane. With older chips, the bonding wires would have been visible here. Now they are using the through silicon wires also here. Yeah. Let's go to the next sample. The next topic I would like to address is a problem that touches most of Earth. It's the aging of lithium-ion batteries. It results in decreasing capacity and therefore faster discharge mobile devices. With Nano-CT, we now want to investigate the microstructure of the battery electrode and the processes on this size scale. Here, we are bridging the gap between simulations and macroscopically observed properties. Here we see the 3D visualization of the scan of the active phase of a lithium electrode. Again, this is a commercially available battery from which we extracted our sample. In principle, a battery electrode consists of a porous bulk of more or less spherical particles that are stuck together. What happens during the lifespan of a battery is that the cyclical charging and discharging process lead to a chemomechanical stress in the active particles. In the long run, this stress can lead to a bursting of the spherical particles. Now, let's clean up the visualization a bit so we can see more of the inside of the sample. The evaluation of the scanned sample now mainly consists of finding the broken particles in the material. The degree of damage and the proportion of broken particles serves us as a benchmark for the life state of the battery. In this way, we try to understand more about the internal processes. If we now look at our displayed volume, we find a large number of undamaged particles. However, we already see some spheres with a moderate level of damage, and we are seeing a few spheres that are already broken internally. With different samples at different stages of aging, we can now obtain statistics on the number and distribution of the damaged particles. This provides valuable information for the further development of the composition. This type of research has so far been carried out mainly at synchrotron facilities, but we have now produced comparable measurements in our laboratory. So let's go to the next sample. As a third example, I would like to show you a sample from the current research on functional materials. This class of materials usually consists of composites of very different components, and the external characteristics are determined by the 3D microstructure. Here, too, the research depends on an insight into the microscopic processes in the material. The example here is a prime candidate for a conductor track material that is not only flexible, but also extremely stretchable, while at the same time retaining its conductivity. One possible application is in the trend sector, soft and wearable electronic devices. It consists of a highly flexible, non-conductive polymer matrix filled with flake-shaped metallic particles The distribution and orientation of the particles is now crucial. And the conductivity results from the fact that the particles touch each other at certain points or come close enough that the electrons can pass over. In the SEM image here, the metallic flakes are clearly visible. Each flake has a diameter of about 100 nanometer. However, to obtain statistics about the flake distribution and orientation of the flakes, it is necessary to have more than just a single image. So, to give you a feeling of what a typical Nano-CT sample looks like for us, here is a picture of the sample. The sample usually has a diameter of about 100 microns and is mounted on a needle tip. In the 3D rendering of the CT scan, you can see the individual cornflake-shaped metal particles, as in the SEM picture before. The sample shown here was previously aged in thousands of load cycles, which led to a reorientation of the filler particles. To observe this reorientation, it is worth taking a look inside. We now see how the particles have realigned themselves. And now, to better understand the mechanism behind the conductivity, it is now possible to identify the percolation path in the sample and trace the connections. Additionally, we can look at the self-assembly of the material. And we can define regions where the particles have compacted and aligned themselves. At the same time, also non-conducting areas have developed. So, furthermore, the migration of the individual particles can then be traced, and the comparison between samples from different material compositions and the different influence on them becomes very interesting. With this information, the improvement and further development of the material can now be advanced. Okay, this was the third example of current materials research at the chair of X-ray microscopy with the NT-CT Nano-CT. Thank you very much for your attention and also for the possibility for me to give this presentation here, today in this context. My name is Dominik Müller, and you are welcome to contact me at any time with there are questions about this presentation or the applications. You can also find my contact details in the invitation email. And now I'm returning to you, Emil.
Thank you very much, Dominic, and thank you for building such an impressive home studio. It's been time, or the time has come for the last speaker of this webinar, which will be Nicholas Westphal from the company Procon X-ray, who will tell us about how you could get one of these systems for your lab. So the floor is yours, Nicholas. Take it away.
Hello everybody, my name is Nicholas from Procon X-ray, and I would like to tell you a little bit of our company. Thank you, Dominic, for these nice examples of application which are possible to do with this system. So Procon X-ray is founded in 2004, and we are only focused on CT systems. So we are not doing anything by type, so we are only focused on CT. And our mission is to find individual solutions for our customers and not build big series of products. So we are building very special and unique equipment. We are located in the north of Germany, near Hanover. So we are doing highest quality made in Germany. So we are connected to the Fraunhofer Group. That we are trying to talk to them for new inventions and what we think is interesting for the industries or for the academic research, and take these developments and bring it to a product which we can offer to the industries or to the universities or whoever who need it. and do a complete product with all these things around. So to build this equipment, do the installation, do the customer care support, do the service, and all these, which is all also to do with such a equipment. So we are also connected to cabinet production site, and of course we have our worldwide distributor network with distributors in the most countries of the world. Just to give you a very short impression of our available systems, so we are starting from very small systems like the CT Portable, which is easily to carry around by one person, going across larger systems like CT Mini or CT Compact, which are still benchtop based, or larger systems which can be full customable. So, for example, this picture of the CT of our CT portal is in total 5 meters high and was developed for scanning very long drill cores. The CT Alpha is the name for all floor stand models, and so when we integrate this anti-CT, the concept which was developed by Fraunhofer with all these special features which makes it possible to scan very easy in that high resolution, we would call this CT Alpha with the option nanotube. So this is the system, and next to it you can see just again the 150 nanometer spatial resolution, which is an outstanding performance for such a kind of CT system, and which can really help to improve your resolution and to see what was invisible in before. That's all I have to say from my side here. So it was very short. Thank you very much for that. So if you have some commercial interest in buying such a system, you can get in contact to me. You can just contact me at sales@procon, or you will also find my personal email address in the flyer and at the end of the presentation. And of course, I'm also here for any question you might have. But of course, you can also ask all of my other colleagues if there's actually something which is interesting for you. Thank you very much for your attention.
Thank you very much, Nicholas. So we have reached the end of the webinar, but before we'll let you go, we will also have a Q&A session with the speakers. So if I could please ask all the panelists to turn their cameras back on. And we have received questions from some of you during the webinar, and we hope to lift a few of those. I should also say that if you have further questions, just drop us an email. I have put up all the email addresses for all the panelists here as well. But let's get started. So I think the first two questions would be for you, Dominic. The first one being the examples you showed. What would be the typical acquisition times for those scans?
Yes, we mostly begin with a rough scan with about 1 micrometer sampling, starting below 30 minutes to get a first impression of our sample. Then you can do a medium resolution scan with 500 nanometer in about 2 hours. And then for the previously shown high resolution scans, it took us 8 hours measuring time. Sometimes when you have a really valuable sample and want the best possible scan, we measure up to 12 hours.
Okay, I see. So a little bit depending on resolution. So for the SD card example, then you mentioned that the sampling was 100 nanometers, and then you said that the resolution was 150 nanometers. So we had a question on how these two relates and what does this mean?
Yeah, this is an excellent question. It actually becomes clearer with the second sample of the material composite when you compare these scans. The 150 nanometer resolution is the one we determined with a test pattern and an MTF evaluation. It is based on the visibility of periodic structures. If you want to see standalone features in your sample, then they can even be a little bit smaller and still give you enough contrast. You can compare this macroscopically with a gap between two plates. Even if this gap is too small to see with your bare eye, you can see the light that passes through this gap when it is illuminated from behind. I hope that I could make some sense out of it.
No, I understand. And then a question which I think is best for you, Christian. So that's a question on that there are several Nano-CT systems out there, and how would you compare this one to all the others?
Well, good question. So we, of course, always also interested in the answer. So my colleague Simon Zabler, he did a round-robin study where he compared different commercial available systems with the NT-CT and written this paper. And even through this study was done with the N1 version of the nanotube, we were very happy with the results.
Cool. So for that people are interested really much in the details, they can go to this paper to have a look.
Yeah.
Okay. And then the last question of the day would be for you, Nicholas. So there have been a lot of people asking if it's possible to do a demo of the system, or maybe rather in these days, if it's possible to send samples to have scanned.
Yes, of course, this is possible. So, and of course, we would be very happy to show the capabilities of the system at your samples. And so, in the actual situation, we would really like to do it that way, that we would first, you can write me an email, and I would like to set up a first web meeting to discuss about your sample and what you want to see, and how we can arrange the scan. Afterwards, you can ship the sample to us, and when the scan is done, we can meet in another web meeting to discuss the results. Or if the situation is getting better, which I really hope, then we can also have a live meeting at the system to see it in natural.
Perfect. Yeah, let's all hope that the situation gets better so that we can do live meetings and live seminars in the future soon. But I think with that was the time we had for today. So I'd like to thank everybody for attending this webinar, and I hope to see you again for future webinars in this webinar series. So thank you to all that attended. Thank you to all our panelists for coming to share your insights, and well, see you next time. Bye.
Bye-bye. Thank you, Emil.
Bye. Thank you.
Bye.